Okay, so welcome back to, what is that? This is not solid state physics. This is Introduction to Scientific Computing with Python. I hope you hear me. Yes, very good. Aircon is also on. So first things first, announcement. I hope you can see. And the announcement is we will have our midterm in 2 weeks' time. When I check the calendar, is that right? It's the 1st of April? It's the 1st of April in 2 weeks, right? So, right, but the midterm is no joke. It's very serious business, right? It will be 50% of your grade. I do not rescale my exams, so it is what it is. The worst thing that what you can do is not show up for no excuse, right? Or cheat or whatsoever, because then you get like 0 points. If you are sick, you go to a doctor, a physician, the physician writes you a letter, oh, that student is sick. And then you either give the letter to me, or I don't give, but show to me, or you submit it to the online system, and then you repeat the exam, no problem, or midterm. But without that, it's just a fail, okay? So, midterm, 1st of April. And again, no joke, I'm serious, as usual. It will be from 9:10 to 11:40. That equals to 3 lecture hours. One lecture hour is 50 minutes. So that should be a total of 150 minutes. Okay, the exam will be on site. Again, if you don't show up, if you think you can do it at home, because yes, we will use Cyber University again. So in principle, you can just log in, but if you're not here, right, we track your student ID. If you're not show up, it's also fair, 0 points. So the regular students. So regular mean, well, you are kind of regular students here, right? But those who take the course for the first time, those that could sign up within the 50 slots we have initially, right? Those come here. The others, right? The ones that repeat, the ones that needed to get my signature to sign in to enroll for this course, please, right? Bring your own laptop as we agreed on. So you bring your own laptop and then we place you somewhere else. At the moment, we also will try to get PC02, which is the adjoint room, so next door. No promises there. It's a closed book format, so the moment you open Google or ChatGPT or Bing or whatever, and I see that, that's a fail, right? Or your phone, or you ask your neighbor. Um, by the way, it will not be helpful to ask your neighbor, right? I can make sure of this. Good. What else? I think it's good if I allow one cheat sheet. So this cheat sheet, one-sided, A4, self-written, you can write down whatever you like. You can bring this, you can use it. Your neighbor cannot use it, of course. But so, yeah. Okay, you have questions so far? All right. One more moment for questions. If there are no more questions, then, oh yeah, this is a good question. Thank you. The style of the exam will be similar to the practice and home assignments. Very good question. And that's basically it. Okay, then we can continue. So last time, as a reminder, we started looking into NumPy, right, which is the numerical package for Python. And we already said, hey, why do we use NumPy? Well, for our numerics, it's just faster. It also will be shown that it will be more convenient to use. And all of that is then actually the basis for other packages. SciPy, scientific computer. Parts of pandas are built on NumPy. Parts of scikit-learn are built on NumPy. So everything is still a little bit slow. Still downloading my own file. Good. So I showed you how to import a NumPy, and we also imported the plotting library matplotlib. Well, not the entire one, only the part that is pyplot. We checked the version numbers. Let's see if this is still up to date. No, I have version 124.3 now. Okay, so you should have the same version. Last time we checked that as well. We went into the array object and looked at some of its attributes, size, dimension, rank. Right, and we had a discussion on the data types in NumPy arrays. And one very important part now of NumPy is that NumPy uses homogeneous data structures. By contrast, lists could use mixed or heterogeneous data structures. So this is very, very different. It brings advantages, it brings disadvantages. And then please go back, look at the example where we discussed this. For example, when I provide a character and a number to a NumPy array, it will make them both or convert them both to an array of characters. Okay, so now the download here should be done. Open my slides, yes, like this. Okay, so now look into this example. We have three arrays, array 0, array 2, array 1, array 2, array 3, and all contain 6 numbers. 1, 2, 3, 4, 5, 6. Note the number and the orientation of the square brackets in the function called array. We use a nested list. You recognize this through 2 square brackets. The difference between array 01 and array 02 is that the nested list, there's only one nested list in array 1, whereas there are 2 lists inside the big list in array 2. When these arrays are then converted into NumPy objects, so these lists converted into NumPy array objects, it's quite different. So in the first part, we have just one row, whereas in the second part, we get 2 rows. Right, and now you should recall your basic math, linear algebra. Hey, this looks like a 1/6 matrix or a 2/3 matrix, depending on how I arrange the brackets in my nested list here. So, but now your question, hey, I always use a nested list. Can I also just use one unnested list? Yes, you can. Then it looks like the example on the bottom. So this is just one row, and it's not really 1/6 or 6/1. It's just list of elements in an array. Later on, we would actually identify this as a vector. Down here, we print the size. All 3 arrays have the same size, 6. And the size is not like, hey, what shape is my matrix or what shape is the array? The size here is just the number of elements. Okay, so here's a little bit explanation on this. Here we have defined 2 matrices. For instance, the first reads 1, 2, 3, 4, 5, 6. The other one reads 2 by 3 matrix, 1, 2, 3, 4, 5, 6. The first number in the tuple refers to the number of rows and the second index to the number of columns. Array of 3 is somewhat different, which can be seen in its rank and size. So the rank of the matrix is given here. Array 1 has rank 2. So it's a 2-dimensional matrix. Array 2 has the same rank. And remember, they all have the same size because they all contained 6 elements. But the rank in array or matrix 3 is different. It's only 1 because it's a 1-dimensional matrix, so it's actually just a vector. Shall we play around with this a little bit? Maybe we could. So then we can scroll down here, just set up the environment to know the vectors. Yes, very good. Go down here. And this is where we are. So escape B. So let's make a new array. Array, maybe a little bit small. Array of 4. See what array of 4 should be. NumPy dot array. This is how we call the method array to create an array. We pass a sequence. If it is one list, then we can just get a vector. So if 5 is missing, so far so good. You can check what's now in array 4, and you will see this is actually identical to array 3. So where the rank and the shape are identical. Well, we had this just now. Okay, so if we now call, for example, the rank, oh, that is 1, and the rank of array 3 is also 1. So far so good, right? How about we change this a little bit? We put 1 square bracket around our sequence that we passed first to array. Now we get a matrix, right? 1 by 6. So this is rank 2. But in principle, I don't have to stop there. I can always add more brackets. Rank 3. So I'm at a 3-dimensional matrix, 1 by 1 by 6. I can increase this. Do you see that? I could do this all day long. So why is this useful? Well, this is a little bit, well, depending on how you build your data structures, right? It's more or less useful or unuseful. However, a vector, yes, we're using this in science and engineering all the time. So that would be rank 1. A matrix you have seen before. That would be rank 2. A tensor you also should have seen before. That would be rank 3 and above. And then you have mathematical fields that use tensors a lot. For example, a simple cross product can be rewritten as a tensor product. We can go into, well, neural networks tensor networks use a lot of tensors, obviously. But okay, so we know how the square brackets now work in the array method. We built an n-dimensional array, right? And the data type is n. Good. So what else can we do? We actually can ask now the shape. One by one by one by six, right? If we enter a nested structure inside our square brackets, we change the shape. So now 1 by 1 by 2 by 3. And I even could divide this a little bit more if I would have more array elements. Anyhow. Okay, one more. Okay, it's however not very convenient to go to the function definition and play around with the number of square brackets all the time, right? It's a little bit boring, it's a little bit tedious. So what we can do instead is to use reshape. I think as a tuple actually. Right. So we can reshape the elements here and then just ask what is the shape. So that's now 6 by 1. We could have 6 by nothing. That would be our vector. We could have 2 by 3. Right? Can you follow? So I'm putting basically different shapes to the numbers and call this a matrix of 2 by 3, 3 by 2. So far so good, right? Now what will happen when I put here in 3 by 3? I want to have it in a square matrix. Okay or not? QI, QI. Not working, right? Because I have 6 numbers and I want to put them in a 3 by 3 matrix. How many numbers has a 3 by 3 matrix? 9. So I have 3 numbers missing, right? That takes very long. Nope. And the error message, I think, is very helpful, right? This is one of the few very clear ones. Cannot reshape an array of size 6, right? We have 6 elements into shape 3 by 3. Obviously, right? So what we can do instead is we take a few of these numbers, we add them into our nested list over here. Then we have 9 numbers and then we can reshape. So far, so good? So next, I have here an example that uses transpose. Shall we play around with transpose to see what it does? Did you ever use the word transpose in the context handling a matrix or vector? Did you do that ever? Have you ever seen the transpose of a matrix? No? No worries. Then today is your lucky day. So we copy here. I copy now array 4. And what I want to do is I want to take whatever's in array 4, reshape it into a square matrix. Okay? And then store this back into array 4. So how do I do this? I reassign the value. Okay? So now my array 4 is that 3 by 3 matrix. And I actually should say still array because in NumPy it's an array, but for us it's a matrix, okay? A matrix. So please look at the numbers 1, 2, 3, 4, 5, 6, and the third row repeats the second row. So far so good? So now transpose. By the way, what's the first thing you do when you find a new function? You check if there's a documentation available with a magic symbol, right? Does not sound very promising here. So what do we do then? Transpose. What happened? Do you remember how A4 looked before? So 1, 2, 3, okay. 1, 4, 4, this is not the same, right? But if I go from left to right in the first array 4, and if I go from top to bottom in the transposed array 4, then I see 1, 2, 3, 1, 2, 3. Okay. So in the transposed one, I flip the matrix around its diagonal. Right? So the transposed of a matrix. So far, so good. Okay, sometimes when we have a non-square matrix, try slowly. Well, matrix 3 is maybe not a good example for now. Here's a non-square matrix. Here is a non-square matrix transposed, right? And then we basically have a 2 by 3 matrix, and we switch that into a 3 by 2 matrix because we, again, transpose. So far, so good. So if you have a non-diagonal matrix, you don't flip around the diagonal, of course, you switch rows into columns and columns into rows. Okay, good, easy. Okay, let's check if this is still working. Now we check the output. So area 1 shape, this is 1 and 6. Area 2 shape is 2 and 3. Yes, fits. Area 3 shape is 6. Transpose area 3 shape is 6 as well. Isn't that weird? Just now we saw, right? Shape give us the shape of a matrix, 1 by 2, 2 by 1, and so on. When I asked for the shape of array 1, right? Array 1 gives me 1 and 6. Let's see what we do in the transposed case over here. Oh, sorry. Transpose again. I want to, what the, okay, slowly. Yes. So now watch the first line. Oh, they swapped. 6 became 1 and 1 became 6, right? Because I have a 1 by 6 matrix. I transpose that, becomes a 6 by 1 matrix from row to column. What's happening in array 3? Do you remember array 3? Array 3 were like the numbers from 9 to I don't know, 4 or so, going backwards. 6 numbers, I have 6, my size is 6, my shape is 6. I transpose, shouldn't I get the same? Well, I mentioned very, very briefly that array 3 is actually what we identify as a vector because it has rank 1, right? So we have 9, 8, 7, 6, 5, 4 over here. That is what we have. The rank is 1, right? So the rank is 1. We only have one dimension. So we don't distinguish between rows and columns. Is 6 times 1 matrix has 6 rows and 1 column. That still counts as 2 dimensions, right? 6 down, 1 to the side. A rank 1 object doesn't have this. It's because it has only just have like 6 elements, right? It has not the distinction between rows and columns because you need 2 dimensions for this. So when we ask the transpose of this vector, there is no transpose, or the transpose is identical in that sense. So far, so good? Okay. Be very, very careful with this. Mixing up vectors, matrix, and vector matrix multiplication on the computer is a little bit a common mistake. And then you wonder what went wrong, where. Not keeping track on when you need to have a rank 2 object and a rank 1 object could be one of the mistakes. Okay. If that is easy, remind a rank of a matrix. Well, let's go through. The rank of a matrix is the dimension of the vector space generated or spanned by its columns. So it's really about how many different principal components I actually can find. Yeah. Okay, what is the meaning of an array shape 4, 1? So this is the question here. Do you see this? We have a similar notation over here. Shape 6, 1. The in-class question is, what is the meaning of an array shape of 4, 1? So what do you think? Yeah, difficult for me to decide today. Curtis, what do you think? Are you still paying attention? Well, is it a scalar, is it a vector, or is it a matrix? What do we know? Is it a tensor? No. Is it a scalar? No. Is it a matrix? No. It's a vector. Very good. It's a vector with 4 components. Could be x, y, z, and time, right? Okay. Now think of a vector of length n as a matrix of shape 1 times n row vectors, or n times 1 column vector. Now, right, so we think about this vector. We want to make use of this. So what we do is, how about we reshape our array 3? How do we want to make it a row vector or column vector? I don't know. Let's start with something. So this is now 6, 1, and according to the nodes, that should be a column vector. And if we change this, 1, 6, this is the row vector. So far, so good. Too fast now? If you want to see what's going on, right, you just remove shape, the attribute here. This is our row vector. 1, 6. This is our column vector. So far, so good? Yes, no, maybe? Okay. So we have rows, we have columns. However, be a little bit careful. So for us humans on pen and paper, row vectors and column vectors, right? We know vector matrix multiplications, and in principle, a vector matrix multiplication is nothing else as a matrix multiplication, just that one of the components of one of the matrices has dimension 1. So we have 1 by 3 matrix times a 3 by 3 matrix, right? It's a vector matrix multiplication or matrix multiplication. Again, be a little bit more careful when you handle your data structures within NumPy. You can always reshape, right, your vectors to an array of rank 2, or you can keep it as a rank 1 object. Right? It's all in the reshape method here. Okay. So the more I repeat it now, I think the more confusing it will get. To sum it up a little bit, you can set up your array objects. You can ask attributes, shape, size, rank. You can reshape, and you can transpose. Okay. Can you assign a matrix of rank 3 and shape 3 by 3 by 3? So rank 3 means 3 dimensions, right? So not a one-dimensional matrix, not 2, but 3. So we have a tensor. And then can have a 3-dimensional tensor rank, shape 3 times 3 times 3, so 27 elements. Who think it can? If you think it cannot, don't raise your hand. Okay? Now if you think it can, don't raise your hand. I think I lost my audience today. Is it too early? I'm also very tired, but I don't have a choice. Shall we make it differently? Can we have a matrix of rank 2 with a shape 2 by 2? Yes, easy, right? So a 2 by 2 matrix is A, B, C, D, and we have one dimension this way and one dimension this way, right? So now, can we have a rank 3? Well, if we have a 2 by 2 matrix and this is one dimension, so from left to right, and from top to bottom is the other dimension, then we have one more dimension, right? From back to front. So we could have already said that my 2 by 2 matrix, if we make it rank 3, would be 2 by 2 by 1, right? How about instead of having one matrix, right, we copy that matrix and put it behind the other one in space. Then we would have 2 by 2 by 2, right? Because 2 by 2 by 2 is like 2 by 2 is 4. 4 times 2 is 8. We need 8 elements. And if we count A, B, C, D, that's a 1, 4. And then we go one matrix further down, right, in space or forward. And that's another, because we copy it, A, B, C, D. That's another 4 elements. So it fits, okay? So now 3 by 3 matrix. In rank 2, we can have 3 by 3, right? A, B, C, D, E, F. And then what letters do I have? A, B, C, D, E, F, G. I really want to include you. And letters are not my strong side this morning. So what comes after A, B, C? What comes after A, B, C? D, right? And then? Don't leave me hanging here. A, B, C, D, E, F, G, right? And then H, I, J. Very good. So now we have 9 letters, right? Okay, and then we copy that, right, and put it back and front. So we have one in front, one in the middle, one at the back. That would now be 3 by 3 by 3 matrix, right? Because I have 3 dimensions. I have rank 3. Okay. So you all seem very interested in my letter matrix. So why don't we... Now I'm going to push this through, okay? So how do we do this? So how do I convert a number into letters? Do you remember Unix code? What was it, 96? So obviously we want the character. What was letter A again? Do you remember? You don't remember, and here's the thing is, I also don't remember, but I know where to get it from. Okay, so I call this my start, okay? So far so good. So start is now whatever A is. And then I can, I go into a list comprehension that we saw last time, and I say, hey, I want to have my letters, the character from whatever I is, and I runs in, well, range from start. Now, I want to have 3 by 3, right? So my end shall be start plus 3 times 3 times 3, okay? And that is put into my list comprehension. But now I get the list, I want an array, right? So I put my list into NumPy array. So what will this give me? This, if I'm not mistaken, will give me a vector of 27 elements, which are all letters from A to whatever letter that is. That's not what I want to have. I want a rank 3 object. So I need to reshape this, right, in form of 3, 3, 3. And if this is now working, always for I in, always forget the in when I type here with a microphone in my hand. Invalid syntax, perhaps forgot a comma. I did not forget a comma. It must be somewhere else. See, I just want a list. Yes, I forgot the comma. I did forget a comma. No, I didn't. Yes, it's early a little bit. This one. And the I comes here. Okay, there we go. A, B, C, D, E, F, G. The thing is, we run out of letters at the end because we didn't copy. So far, so good. So this is now in array. We have 1, 2, 3 opening square brackets. So most likely this is rank 3. We can check with ndim, number of dimensions, 3. So far, so good. Now, in principle, I can, yeah, it's okay. For there we go. So this would be the result of our list comprehension, just a list, right? And this list is passed on to the array and reshaped. If we play around with this argument here, range, we actually can make sure this is just a repetition of our 3 by 3 matrices inside that bigger list, but this is how it would go. So now after verifying with letters, Yes, we can have a matrix of rank 3 with shape 3 by 3 by 3. So far, so good? Okay. Here's another example. Will be hard code a little bit. So let's see, we have just an array that is a vector because it's just one list. Then I repeat this 3 times, put it in a nested list, so I get a 3 by 3 matrix, rank 2. I repeat this one more time, right? Then I get 3 by 3 by 3 shape with 27 elements. So size is 27 and NM is 3. So what else? So in principle, we can now, we have everything we need to implement the Levi-Civita symbol. Levi-Civita symbol. It's a very useful notation of a matrix that basically says, hey, I'm either 1 or -1 or 0, depending if my number elements, so epsilon, where the indices I and j, if it is 1 and 2, it's +1. If it's 2 and 1, it's -1. If it's equal, it's 0. So you can find a little bit more on the Wikipedia site. It will explain to you, and this is normally a good home assignment. Implement Levi-Civita symbol yourself. There are many different ways of doing this. One is hard coding. That's fine. You can do it a little bit clever. You can use a nested for loop, or you can use some functional definition. So in 3 dimensions, it's a little bit more complicated, but the logic follows the same. If elements are identical, like on the diagonal, in one or the other pair of dimensions, it's 0. If not, it's either -1 or +1. Right? And if you look carefully, there are like cyclic or anti-cyclic permutations of the indices that define if it's -1 or +1. So that is something you can try yourself. And it's a nice exercise from, hey, here's my problem. How do I implement it? Because you have the tools already available to succeed. All right, so here's the task. Implement the Levi-Civita symbol. Do you want to do it in class or at home? If you want to do it at home, don't raise your hand. So many, okay. So that will be home assignment. Very good. However, yeah, here's the solution. Here's my solution of this. Obviously, this just will be, how you say, orientation. So in the home assignment, we make it a little bit more challenging. Okay? Good. So we reach the end of the first section, which is just setting up NumPy array objects. Comprehension questions to see if you went through the course book, if you went through the course literature, course notes as well. So let's read together, although I know you can read yourself. What does n bytes attributes stands for? Can you assign a matrix of rank 3 and shape 3 by 3? Yes, we did this extensively. How can we define vectors and matrices using NumPy? So I hope you can answer all of these questions, because at least one of them we discussed extensively together. The other ones, here the answer is one of the tables I give you. And the last one we discussed like in the middle of today's first lecture. And the last row I think I should remove. I think this one I should remove. Because it's just about the rows and vector sizes. Okay, questions so far? Well, then it is soon time for a break. I see this strongly repeated there. So lastly, some difference between column and row vectors can be given as follows. So there we have a column vector, sorry, row vector. Below we have a column vector, and we see that different, although they're actually matrices here. Okay. Now really, comments or questions? If not, then it is time for a break. I will make a note to put the Levi-Civita symbol as a home assignment, as you all selected it. And then, yeah, we continue in 10 minutes.